G'day everyone, my name is Maini Sitani, a solutions architect from Amazon Web Services based in Australia. Welcome! In this session, we'll show you best practices in architecting your container workloads for 10x faster performance and less service interruptions so you can get some great night's sleep. Now today, I'm joined by my colleague Mitch Beaumont, who is a principal solutions architect and a container subject matter expert. We also have Peter Keim, who's a senior DevOps engineer from Domain Group, which is one of Australia's leading enterprise in the real estate industry. So I'm super excited to have them on board. So you're probably wondering why this font looks like a game. And that's because I've simulated a game called Well-Architected Containers, and I want you to play along with me. The objective of this game is to collect all 5 keys to the pillars of Well-Architected so you can have faster, more reliable, secure, cost-optimized, and operationally excellent containerized workloads. I'll start off with some tips and tricks in optimizing your container architecture. Then Mitch will run through a demo of what this looks like in a DevOps environment. And Peter from Domain Group will talk about their journey from Amazon EC2 to a fully managed containerized solution with Amazon ECS, and some well-architected improvements they made along the way. And to wrap up, I'll show you some great resources so you can start building your very own well-architected containers. Now let's get started on this game. In this game, I'm working at a fictional company where I'm running containers on Amazon ECS on EC2 and AWS Fargate, which is our serverless compute engine for containers. The aim of this game is to collect all 5 keys to the pillars of Well-Architected, remember? Well, great. I'm going to play as a character in the DevOps team for this game. Finance is here and they want to reduce our AWS costs. So how do we find our first key to cost optimization? For Amazon ECS on EC2, you can save up to 90% compared to on-demand by using spot instances. Spot instances makes use of spare capacity that's available for use within the cloud. You can add Spot to your existing on-demand fleet to increase your capacity and handle peak load. Our customer Domain Group will talk about how they saved in costs using cloud-native tools. And what about AWS Fargate? The great thing about Fargate is that you don't have to run full Amazon EC2 instances. You only pay for what you use, such as the amount of CPU and memory that's consumed by your containerized applications. You can also blend Fargate Spot to cover for peak capacity and save even more on costs. Now let's dive deeper into this concept. There's a variety of purchase models that you can use, and spot instances here in blue are perfect for scaling temporary, stateless workloads. On-demand is great for stateful workloads, and savings plans for steady state. Now the compute savings plans that covers Amazon ECS on EC2 and Fargate is great for cost optimizing your container environment. It offers additional savings of up to 66% for a commitment to using a specific dollar amount per hour for a 1 or a 3-year term. Now let's have a look at what a cost-optimized container architecture looks like for Amazon ECS on EC2. We have instances spread across multiple availability zones and an auto-scaling group for resilience. You can also mix and match on-demand and spot instances. Now this means you have the flexibility of running multiple container workloads within the one ECS cluster, while also saving costs with Spot. Cybersecurity have arrived, and they want to secure our containers from vulnerabilities. So how do we find this second key to being secure in our well-architected game? We can start using Amazon Elastic Container Registry to scan images to identify software vulnerabilities. Now to get this key for security, you need to scan the images in Amazon ECR and check and remediate these vulnerabilities before using this image within the ECS cluster. And this is all automated with continuous integration and deployment with AWS Code Pipeline. You can see all of this in action in the upcoming demo in stage 2 of this game. Now this is what the container image scanning dashboard looks like. You can see the different severities of vulnerabilities which are color-coded from critical all the way to informational. Each vulnerability has a link to the common vulnerabilities and exposures page to show you details of what needs to be resolved, as well as the package name so you can prioritize any risks to your workloads. And it's easy to enable ECR container image scanning. You can do this with just one click on the AWS console, and it's configurable via API. Marketing says that we have an upcoming event where we're expecting a lot of traffic. I know last time we ran out of capacity because we didn't have enough instances running to handle this peak traffic. So we had to continuously monitor our ECS environment and manually adjust the number of instances in our auto-scaling group. So how do we find this key for reliability? Capacity providers manage the scaling of your infrastructure on your behalf within an ECS cluster. How is that different from EC2 autoscaling? With EC2 autoscaling, you had to continuously tweak your configuration. You had to take an infrastructure-first approach. With capacity providers, you can think of your application first. Your infrastructure responds to your application's needs. So if your application needs 6 tasks, which is a collection of containers, then capacity providers works with your EC2 autoscaling group at the cluster level to respond with enough EC2 instances to run your tasks and services. This way, you know your application is built to be reliable without having that complexity of managing EC2 autoscaling groups, and it reduces your undifferentiated heavy lifting. Our IT manager is looking for metrics for her weekly reports to the CTO around the performance of our containers. Amazon CloudWatch Container Insights analyzes performance trends and helps you automate your developer workflows. How does CloudWatch Container Insights help? You can dive deep into your infrastructure through detailed structure logs and metrics. Automatically alarm and scale based on events such as network and storage utilization or service and cluster state. Reduce risks by implementing tooling to respond to unexpected performance changes. Now, as you can see within this diagram, we have a sidecar architecture. The application is talking to the metric sidecar container. Now, both of these containers have the CloudWatch agent installed, so you can see detailed metrics around your application and your control plane. Now, the beauty of this is that you can benefit from seeing your container and application metrics in one place in real time via Amazon CloudWatch Container Insights. On a typical CloudWatch Container Insights dashboard, you'll see metrics such as CPU and memory utilization, the number of running and pending tasks, and the number of deployments. Congratulations, we've cleared stage 1 and collected all 4 keys to a well-architected containers environment. Our DevOps team achieved cost savings by using spot instances and savings plans. We improved security with ECR container image scanning by detecting and mitigating vulnerabilities. We enhanced reliability with ECS capacity providers as it responds to our application with more infrastructure. Performance went up as we're monitoring real-time metrics with CloudWatch Container Insights. But wait, we're missing the 5th key. This game is far from being over. In the next stage, Mitch will run a demo in a CI/CD pipeline as part of the 5th pillar, operational excellence. So stay tuned. And I'm handing over to Mitch right now.
Thank you very much, Mai, and thanks everyone for joining the session today. My name is Mitch Beaumont, and as Mai said, I'm a Principal Solutions Architect at AWS based in Sydney, Australia. And I'm going to talk to you over the next few minutes about the operational excellence pillar and how that relates to the architectures that Mai has already talked to you about. If we think about operational excellence in the context of the AWS well-architected framework, there are 5 design principles that we hold near and dear. They are performing operations as code, making frequent, small and reversible changes to our software, refining our operational procedures frequently, anticipating failure and learning from all of our operational failures. Now on the screen you can see a small architecture that I've put together that represents a CI/CD pipeline for a containerized application. And I'm going to show you now how we can use this pipeline to really drive home the releasing small, frequent and reversible changes using a concept called blue-green deployments. So in this demo, we've got a simple pipeline that we've created using AWS Code Pipeline. It deploys a simple application, a cat meme sharing website with a green background. Now I want to change the background to be red. That's going to be the new version of my application. So here you can see I'm going into my GitHub repository. I'm making a change to the HTML, and I'm changing the background to red. And then I'm going to commit those changes directly to the main branch, which is probably not good practice if you're doing this in production, but for the purposes of today's demo, that'll work for us. We can see now that the pipeline has detected those changes, and it's starting to work its way through the different stages. We're first doing an infrastructure deployment check because all of my infrastructure is deployed as code. And then we're going to start to build our container application, taking all of the source code artifacts out of the GitHub repository and scanning them, checking them, assembling them, compiling them, and packaging them up eventually into the container image or a Docker image. Now, as part of this deployment process, we're then going to take our application and we're going to deploy it using a concept called blue-green deployment. And we'll learn a little bit more about how blue-green deployments work over the next few seconds of this video. You can see here now that code pipeline is working its way through the different dependencies that I've defined for my application using standard components within the requirements.txt file, which I have for my application there. We're packaging up the container image, and we're now getting ready to push it to Amazon's Elastic Container Registry, or ECR. We jump back to the code pipeline console now. We can see that we've moved on to the next phase of the deployment, which is to start the blue-green deployment of the application itself. So what is a blue-green deployment? Well, it's a mode of an immutable mode of deploying an application in a way that can hopefully remediate or mitigate many of the risks that are typically associated with deploying software. It does this by creating two parallel environments, a blue environment, which runs the current known working version of the application, and a green environment, which runs the new version of the application. Software engineering teams can use these parallel environments to safely release changes to their applications, test those changes, and gradually shift user traffic from the old version to the new version. And that traffic shifting typically happens using DNS or a load balancer. If during the deployment process, the engineering teams detect problems with the application, or the old version of the application, the new version of the application, which is our green version of the application, or if the users report problems with the application, they can quickly roll back to the previous version of the application because the parallel blue environment is still running there. So essentially reversing those changes to make sure that our application remains available for the customers that are using it. So we can see that this is now working through, and we've started to shift some of the traffic over to the green version of our application, which happens to have a red background. And we can see that this is slowly working its way through in exactly the way that we want it to do. If we jump back now to our console, I'll quickly explain the process that the blue-green deployment is happening in, and that is we're incrementing traffic or shifting traffic in increments of 10% every 1 minute. So this is going to take a few minutes, but it's in the interests of safely deploying software. In the meantime, let's go and now have a look at the ECR Elastic Container Registry container image scanning functionality that Mai talked about a little bit earlier on, and how that integrates with our deployment pipeline. Firstly, I'm going to modify my Docker file, which contains the definition of my container image. I'm going to replace the standard base Ubuntu image that I'm using right now with an image that I know contains security vulnerabilities. My hope is, and obviously I wouldn't suggest you do this in production, but my hope is that I can force our code pipeline to detect that vulnerability through container image scanning and fail so that those changes never make it into production. So again, we can see that now we've committed those changes. Code pipeline has automatically kicked off the workflow again. We're working through the different phases of the deployment process, checking infrastructure changes. Again, my infrastructure is defined as code inside of my repository. And now we're going to move over to the build process, which again is going to be orchestrated by code build. And as with the previous example where we built and launched the red change to our environment, we can see that the code build process is downloading all of our dependencies. And what we're doing with Amazon's Elastic Container Registry, or ECR, is that we're going to push our container image into ECR. And we're going to use one of two different types of configurations that ECR offers. ECR allows us to scan images on push or scan images manually. And pushing this image to Amazon ECR in an automatic scan on push configuration will force that image to be scanned by the open source, the common vulnerabilities and exceptions database provided by the open source Claire project. And we can see now that the container image is being pushed into ECR. And very shortly what we'll see is a set of scripts or commands run to actually scan the image. Very shortly, we should see a response back telling us that a high severity vulnerability has been detected. Wonderful. That's happened exactly as hoped, and the demo gods were shining down on us today. Let's jump back to our pipeline now, and what we should see as part of that build and deployment process is that the build fails, which is what we want. We don't want to release our software into production if there are vulnerabilities contained within it. Good stuff. Let's jump back now to our pipeline. Let's see how our deployment process is going. And what we can see here is that we're now with roughly 20% of our traffic going to our blue environment, our old environment, and roughly 80% going to our green environment, which also happens to have a red background. So my apologies if that is confusing anybody. It wasn't my intention. Under the covers, what's happening here is code deploy is orchestrating the creation of a new set of ECS tasks under the covers and a new ECS service, and orchestrating the gradual rerouting or redirection of user requests from the old version. And if we hop on over to our application, we can see that we're now all hitting the red background version. So we've safely deployed the new version of our cat meme sharing website, which is wonderful. So hopefully what you've seen over the course of the last few slides in the demonstration is that you can safely deploy software using AWS code pipeline, code deploy, and code build in a blue-green way that will reduce the risk of introducing problems into future application deployments. This will hopefully help you all get a good night's sleep. And with that, I'd now like to hand over to Peter so we can talk a little bit more about Domain's journey. Over to you, Peter.
Thanks so much, Mitch and Mai. Just on that point you made about getting a good night's sleep, or not, let me tell you about a time where that happened to me personally. My name is Peter Keim, and I'm from Sydney, Australia, and I'm a DevOps engineer in the Cloud Platforms team at Domain Group. So I was woken up one morning at 2 a.m. due to a failed scaling dependency. And this was the starting point in our journey of embracing the well-architected principles to ensure that this never happens again. I'm really happy to have this opportunity to talk to you today about our experience utilizing the well-architected principles to uplift and improve some of our service offerings using Amazon ECS. But most important of all, how I managed to get a good night's sleep, as this journey began at 2 a.m. that morning when I received a wake-up call because of a service outage caused by failing dependencies. But first, let me introduce Domain. We are a real estate, media, and technology services business. Our Australian viewers will know us best from our real estate listings portal and our media articles. And as one of our tech leadership team often likes to call out, we can be seen quite literally on the side of a bus. But I'll add to that we're also at the bus stop and on a tram. Now, our iOS and Android apps have over 1 million users per month, and these numbers are up 20% when compared to the same time last year. We also feature our product on a reality TV show here in Australia called The Block, where contestants are challenged with renovating rundown property before they are listed on our platform and sold at auction. In addition to being able to reliably support our regular peak time traffic, it is especially important to ensure that our users are getting a good experience whilst we have the aforementioned national TV exposure. Our mobile apps are supported by various back-end API services, and this is where our problem statement is going to center around. So how can we improve our mobile API services and win this game by collecting the 5 keys to the AWS well-architected pillars? So let's start by looking at the current challenges or enemies that we need to face. Firstly, we're running some workloads on older 3rd generation EC2 instances, which are not cost effective when compared to the more recent generations. Next was our auto scaling. It was complex and inefficient and didn't perform at a level we needed it to. To ensure that we had sufficient resources, we needed to set up scheduled scaling based on traffic prediction, which was highly inefficient and costly as it often resulted in unused capacity. We also had a dated and legacy infrastructure as code setup for these services, and it was a bit prone to failure, especially during scaling, as there were a number of build dependencies. All of these things contributed to poor cost optimization, as we were supporting something on older tech that was in dire need of some upgrades and re-architecture. So the solution. Now, before I get to that, I want to go back to that early morning call out I spoke of at the beginning. Now, I do want to strongly emphasize the words early and morning. We had a scaling dependency fail, and because of this, we got stuck in a dreaded auto-heal loop. So the kind of thing you don't want to be dealing with, well, ever, much less at 2 to 3 a.m. in the morning. I came out of this experience knowing that something had to be done, as I was not keen on dealing with this situation ever again. The best way to address this is to ensure that we have 0 dependencies on scaling. We will be using containers on Amazon ECS to host and run these services. We will be building the container image using our well-established build and deploy pipeline, which will allow us to decommission our legacy infrastructure as code setup. This exercise is more than just a lift and shift, and it was never sold as that. This was a transformation, as every component required rethinking, because we can't achieve the desired outcome if we hold on to older processes. And lastly, we wanted to ensure that we had an appropriate scaling strategy that could seamlessly adapt to peaks and troughs in traffic. This is where we engaged Mai and Mitch through our AWS partnership, and we were introduced to manage scaling through the ECS capacity provider. What this will allow us to do is to remove all the auto-scaling group policies that we have and give control to the ECS cluster. And through capacity provider, scale out and scale in will be triggered based on resource requirements. This sounded ideal for us because we have a high workload and we want to scale the cluster based on how many tasks we want to run. So now let's look at the architecture, starting with what it used to look like. As you can see, we had a classic load balancer that would distribute traffic to EC2 instances within an auto-scaling group that had various types of auto-scale policies attached in an attempt to keep up with the traffic demands. And it has an infrastructure as code repository that would be used to configure each of these EC2 instances as they launch. And now this is what we moved to. So now traffic flows through an application load balancer, and now we run these particular services inside containers on an ECS cluster. There is a capacity provider attached to an auto-scaling group to manage the host capacity. We're also making use of CloudWatch Container Insights, which provide valuable insights on the ECS infrastructure and running services. So here are our findings and what we've done to gather the 5 keys of AWS well-architected. Both before, during, and after this transition, we've been using Trusted Advisor to help with the right sizing of our infrastructure. But now that we also have access to container insights, and with a now simplified build and deploy process, we have enabled further improvements such as reducing the cost of load balancer traffic through better caching and using gzip compression. And of course, throughout all of this, we could visualize these outcomes using AWS Cost Explorer to show downward trends on pretty graphs that we can show to leadership teams. Now, because we aren't using Fargate for this particular use case, we need to manage the patching of the supporting EC2 fleet. Rolling out of the latest ECS optimized AMI is a lot easier to automate than we thought, as Amazon will provide the latest image ID in the SSM parameter store. So all we needed to do is have a process that checks it on a regular basis, and if it changed, perform a CloudFormation update. And before we've even noticed, it's likely been rolled out and replaced the old AMI through normal scaling activity. We also have enabled container scanning whenever a new image is published to the Elastic Container Registry to ensure that we aren't introducing any vulnerabilities with an image update. Now, one of the first problems I noticed with the use of Capacity Provider was that although it scaled up to match the demands of traffic, I noticed that it wasn't so good with scaling down. The issue was with the placement strategy. Now, by default, you're going to get a randomly placed task both with addition and removal. In order for a capacity provider to trigger a scale down, it needs to get an empty host, and that's going to be difficult to achieve with a random placement strategy. So what we needed was a bin pack placement strategy, which means that tasks will be placed on the host with the least available resources, meaning that it's trying to fill up the container hosts and take them away from hosts with the most available resources. So it's trying to empty a host instance. So this allowed us to get more efficient usage out of our EC2 host and scale them down when we don't need them. Another problem we found is that when using containers, it means that we're going to have a greater number of them than we would have previously with EC2 instances. And that presented us with a problem, as the increased number of containers meant that the connections to our AWS Elastic Cache also went up, which caused some strain on our cache instance. We were, however, using an older generation of cache instance, and this also needed an upgrade to cope with the increased number of connections. I mentioned that we use CloudWatch container insights so we could track the performance of our containers. And that allowed us to fine-tune our ECS task definition to have the appropriate resource reservation and task count. We also use the container insights to help with the configuration of CloudWatch monitors so we can stop and start additional tasks when necessary. Now, whilst we were able to effectively use Capacity Provider to scale up and down with accordance with traffic, where it didn't quite work out for us was when we wanted to do a deployment. So for example, we're launching a new container image. In order to support a blue-green style deployment, we would suddenly need to scale the cluster to support double the capacity during the cutover. And the Capacity Provider just wasn't adequate to support that. So what did we do to get around that? Initially, while we looked for a better solution, I set up a chatbot in Slack that a developer could run from Slack just prior to deployment, and it would provision the necessary capacity required for deployment, and then leave it for a Capacity Provider to scale it back down afterwards. Although this did solve the problem, it kind of breaks the DevOps landscape of a seamless transition of build, test, and deploy. If you suddenly have to go and chat with a bot before deployment, then it's not so seamless anymore, especially because it requires a human to remember to do it. So what we did was configure CloudFormation to send an SNS notification to a Lambda, which would listen for an update to an ECS service. And if this happens, the Lambda will find out where the request is coming from, and it will provision the capacity required to support the deployment cutover. And then, of course, Capacity Provider will scale it back down afterwards. This allowed us to re-establish that seamless transition of build, test, deploy. And for our outcomes, now as you can see, we have achievements in all 5 of the well-architected pillars. But I do want to pay special attention to the third one, of 0 infrastructure incidents. If this was the only thing that we achieved with this journey, then I would have called it a success, because it was the reason why we started it in the first place, as I certainly didn't want to be fixing any more failed dependencies at 3 AM in the morning. But we also wanted to ensure that our peak time users get the same experience as our non-peak users. And that's probably the biggest achievement with this piece of work. But because we took a holistic approach to this and rethought the entire architecture, we enabled other achievements, such as bringing down the cost, simplifying the patching, speeding up our scaling capabilities, and positioning ourselves to better address organizational priorities. And now for some future items that we plan on doing. We've already jumped on board with CDK to further improve our infrastructure deployments, and we'll be looking to further expand our usage of this. I'm also very keen to try out the new Graviton 2 instances. Obviously, these are ARM-based CPU architecture, so a little bit of work needs to be done on compatibility and testing. But if they can provide the advertised 40% price performance improvements, it'll be well worth it. We can also look at utilizing EC2 Spot to support a percentage of our cluster to save on some EC2 instance costs, but still give us the certainty of on-demand instances to support the bulk of it. I'm also very keen to do a proof of concept of the Bottle Rocket AMI. I have played around with this a little bit and it does look promising. And also looking at applying this similar architecture to other workloads that currently run on older EC2. And that's it from me. We have written a tech blog about this journey, and the link will be in the resource pack. But for now, I'll pass back to Maya to wrap things up.
Thank you, Peter. Now we're at the final stage, and it's time for you to start getting hands-on. Are you looking for some sample code from this session? What about some great tutorials so you can start building your very own well-architected containers? All you need to do is to scan this QR code, which will take you right to our GitHub repo so you can start building. And here are some useful well-architected resources to get you started. On the behalf of AWS and Domain Group, thank you very much for listening. Please complete the survey and keep on building.